Hello, hello. Okay, friends, let me give you explain this master page. Okay, now the master page is mapping master page. Okay, it is also called L1 table. Okay, the master table or L1 table. It is actually mapping the available virtual space we have. Okay, 4 GB of available virtual space. This virtual space, available virtual space of 4 GB is split into 1 MB each. Okay, of 40996 entries. Okay, it varies from 50 to 4095. So each of those 1 MB spaces are split into multiple 1 MB space, and how these virtual spaces, the virtual memory areas, are configured is, and where it is located is represented in the table. Okay, so every 1 MB space of the virtual space has an entry in the table. Okay, so this number of entries are same 4095. Okay, and each of them occupies 4 bytes of space. Each entry is in the table. So totally there will be 16 kilobyte of L1 table. So once we have a table make which will take care of the complete 4 GB space that are available for the programmer, then we can play around with that. We can say that maybe I can keep, you can have anywhere in this, but the physical memory can be anything, limited. Okay, or same physical, virtual space could be mapped to different locations in the physical memory. Okay, based on which process is running. So, for an example, suppose the user is, I told you when it is bottom spaces are always directly mapped, so it may not go to MMU. So it will be, there will be a space in the physical memory. The bottom some locations may be reserved to make sure that it is one-to-one mapping is there, because always the vector table and OS are residing in the bottom address. This is a higher address, so which will be not having a MMU associated with that. Except for that, anything that is ARM generates the virtual addresses coming, they will map to one of the entries in this. And then now that the entry will decide whether it is directly pointing to 1 MB space in the physical memory, or it maps to, it points to a table, another table which is called L2 table, and which gives a minute granularity in terms of access permission of that 1 MB space. See, each entry here of takes care of 1 MB space in the virtual memory. Okay, that 1 MB space could be directly mapped to one location in the physical memory, or it could be going towards with the L2 entry. In this case, what happens is it is split into. Suppose if you are saying that 1 KB pages, then 1 MB will be having how many entries? 1024 entries. So out of 1024 entries, I may decide to have only half of it pointing to the real physical memory, and the rest of the entries may say that you should generate a fault. That means that much of space is not available. Or you can say that all the entries are available, but they have different access permissions. So effectively, as a summary, L1 master table has to be there in the system, and it needs to have the 4096 entries, and it should be physically there in the physical memory. Okay, so that you will know when any of the addresses are generated, whether it is a valid entry or not. Okay, I will explain. That is, suppose one of the virtual addresses is not physically present, we can make an entry here to say that generate a fault if this address is generated. So we have to make sure that all the available 32 addresses are addressed. In the sense, what needs to be done when that kind of address comes, that should be handled. So this L1 master table, that is why it is built as 4K entries, okay, 4K entries of 4 bytes each, so it is 16 kilobyte size, and each of them taking care of 1 MB of space, okay. 1024 KB of page size means 1 MB of section. So that 1 MB physically can be there in the memory, or it could be not there at all. Then you will have a fault entry, or you may point to another table which may give a final granular details about that page, 1 MB section. Now let us not talk about L2 now. Our focus is on L1, and that is what I am addressing now. And just to a continuity sake, let me tell you how these values are mapping. Okay, now you understand why this 4K and why is 16K kilobyte of size, and then you know that it is taking care of 1 MB space. Now let me tell you, in the fine table, if suppose fine table means the size is 1 KB size. Okay, it is taking care of 1 KB size. Okay, so if a table, okay, the L2 table always one L2 table for 1 MB of space, the virtual memory space, 1 MB space. Okay, if I say that each table entry takes care of 1 KB of space, how many will be there? 1000 will be there, right? So 0 to 1023 entries will be there, each of them taking care of 1 KB of size, 1 KB of space size. Okay, now 1 KB of size, it also says that, so 1 KB of size means out of 1024 entries, and I said that one entry takes 4 bytes of space, so it will be 4 kilobyte of page size. Okay, the total L2 page, sorry, this is the L2 table size. L2 table size is 4 kilobyte. Okay, now what happens if the page size is 4? It will be 4 consecutive entries will be giving the same value, will be having the same value of access permission, write buffer, cache behavior, all that. If it is a 64 KB page size, 64 consecutive entries will be assigned with the same entry. That means it will all have the same behavior in terms of one page has to have the same characteristics. I told you, same attributes. So if it is a 64 KB of page size, then we'll have all the 64 entries of 1 kilobyte page sizes will have the same attribute. I will tell you how the attributes are entered in the page table, but that is how it is done. So I hope this page table entries you are able to understand. Now what happens to the course table? Course table means the page sizes are bigger. It is either 4 KB size or 64 KB size. This is also a L2 page, but instead of 1 KB, now the size is changed to 4 KB of size. That means each entry in the page table of L2 table corresponds to 4 KB of size, page size. In that case, 1 MB space will be, how many 4 KB of the entries will be there in 1 MB? 256. Because 1/4 of what you saw in this fine table. That is why you see 256 entries in the L2 table. If the L2 is a course table pointing to a 4 KB page size. In that case, what is the total size you will have? If it is 256 entries into 4 bytes each, it will correspond to 1 KB of size. So that L2 page table size will be 1 KB. And similarly, it also supports the 64 KB pages. That means what? 30. Okay, 16 into 4 is 64. Right? So 16 consecutive entries in the L2 course table will have identical entries to support the 64 KB pages. Okay, similar to what I said about supporting a 4 or 64 in the fine page table. So I hope you understand the entries, different entries, what they correspond to. Let us go forward. Okay. Now there are two levels of page tables, L1 and L2. There is a single L1 page table known as L1 master page, and that can have two types of page table entries. One is it directly connects to a 1 MB space in the physical memory. Any space, any part of the physical virtual memory, 1 MB space, okay, there will be for every 1 MB of virtual space, there is a one entry in the L1 table. That L1 table may have pointing to another section with with 1 MB of physical memory. If all this 1 MB is somewhere, it may be located. That where it is located will be there in the base a value, but it will point to a physical memory of 1 MB. Or it can decide to point to another table, 1 MB of another 1 MB of space in a virtual space, maybe having a one entry which may point to L2 table. That is the next one. It may point to the starting address of L2 table, which will say where that is located and how the behaviors are and what is the phase space of that particular section. So the master L1 page table divides the total available 4G space into 1 MB sections. The available 4G virtual space is split into 1 MB sections. So it will have 4096 page table entries, and that many entries will be there. Now one more thing is, you have to remember that the page tables are always on the boundaries of the sizes. So what I mean by that, suppose okay, let me draw it. Suppose we have L1 master table. Master table itself has to be on 16 KB boundary. That's okay. I will explain in the next question, because the size is 16 KB. As a similarly, L2 fine table size is 4 KB, so it has to be on 4 KB boundary. And L2 post table size is 1 KB, so it has to be on 1 KB boundary. Okay, what I mean by boundary address, you all understand. So let us go to this now. Now, location of L1. Now, as I told you, it is the L1 table has to be in the physical memory somewhere. I can locate it anywhere in the physical memory. Okay, L1 table itself. Okay, but it will be mapped one to one. So there is no need of MMU to access it, but it can be anywhere in the physical memory. It need not be even the lower space. It can be in the higher memory space also. As long as it is mapped directly without MMU, you can access the table. Now, for a discussion sake, let us assume that it is on the lower part of the memory. Okay, typically OS and all tables are lying in the lower end, so the 0 is here. Now, what is the size of L1 table? It is 16 KB, correct? Now, 16 KB occupies how many bits of addresses? You said you know that 1 KB takes 10 bits, correct? 10 bits of address. So 4 KB will be another 2 bits, 12 bits. 16 KB will be 14 bits of address space. So the lower 14 bits will be 0, because anything after that only the address is, because it is on the boundaries of 16 KB. So starting from maybe 4000 hex. Why 4000? The first 3 nibbles will be 12 bits, and then rest of these 2 bits also are 0. So 14 bits are taken care of. So starting from 4, any value pattern you can give in the higher values to locate that 16 KB of L1 page table. Why do we need a register like this? Because this can be accessed using the coprocessor and the hardware MMU. Okay, MMU, while accessing the L1 table, it can easily use this register and keep it here somewhere, and then you can use that address along with the page, whatever address, virtual space is coming. Based on the address, it can index into the table. That is why we need to index into the table. Okay, so for that we need to know where the table is starting at. So the starting address could be physically anywhere, so that is stored in the register. It can't be anywhere else. It has to be in a coprocessor register, so that it can be used by the MMU whenever it wants to access the L1 table. Okay, that is why you are seeing that it is on 15 KB boundary, so it is a lower 14 bits are 0. Okay, I hope this is clear to you. Now let us see the location of L1 master page table in memory is set by writing into this register. So once we decide where we want to keep the L1 page table, that address can be written into this register. Then what happens? Automatically MMU, when it is translating the address, it will get the base address of the L1, and then based on the virtual address that is coming from the processor, it will index into that in table and to find out what is the mapping for that particular virtual address in the physical space. So the CP between C register holds the translation table based address. This is called translation table based register address. And address pointing to the location of the master L1 table virtual memory, which is also same as physical address. I told you that to access the page table, we cannot use the MMU, so it is same as the physical address. L1 needs to be located on 16 KB boundary in memory, where L1 table space is also 16 KB. So one sample instruction is like this. So what is this MCR? We can have some value, okay, either R1 or R2 or anywhere, okay, which is actually having a lower 14 bits having 0, and then the remaining bits are having a some valid address which is pointing at the physical location, physical memory location where the L1 table is starting. And what are these registers? These are the T2C register, and then we are telling that whatever is the register is having that value, take the lower, okay, bits and then use them to access the page table. Who will be accessing the page table? The enemy. Okay, so we are setting up, but entries, page table entries are filled up by the OS. So it has to keep somewhere in the location, main memory, and then it has to say where it has kept the page L1 table in the physical memory by writing into this register. Okay, that's all. Now once this register is pointing at the starting of this address of the page, then the remaining index can be accessed based on this location, and then you may have to multiply by 4 because this, each entry is going to be taking 4 bytes. So the location, the particular entry is accessed. If I will show you each entry corresponds to what, but if suppose the entry has a lower bits as 10, it means a section entry. That means this 1 MB space. What is this 3? 3 is the third 1 MB space. In the virtual memory, first 1 MB, okay, where it is pointing at is given by this entry. Another 1 MB, this this is the virtual space. Another, this is up to 1 MB. This 1 MB, where is it located? Whether it is pointing to the this space is referred to a L2 table and then pointing here, or directly a section entry will be where it is located also will be mentioned here. So this entry is shown, so that means the fourth 1 MB, that is 0 to 1, 0 to 3, starting from this space 4 MB. Okay, this space is what is a section entry. So this address will say this physical address which maps to 3 to 4 MB space is mapped to which part of the physical address is given by this space. Okay, that is why you see that 20 bits are offset is there, because within the 1 MB is what 20 bits will correspond to 1 MB space, so it can index into this 1 MB. So this is how it is mapped. I hope this is clear to you. Okay. Now let us see what are the possible entries. See, it could be a section entry. That means what? It actually says where is that 1 MB is located in this space, and then it will have only one access permission, because all the 1 MB section is treated as the one entry. So it will have access permission here, and the domain is the another level of control. Okay, I will explain shortly. And then what are the behaviors of cache and buffer? And then the lower 10, if it is 10, if the entry has 10 as a lower 2 bits, then the MMU will consider it to be a pointing to a 1 MB section directly. It is not pointing to another entry, page table entry. But if it is a 01 or 11, then it corresponds to a coarse page table or fine page table, which I told you that two L2 tables of different sizes, and coarse table is actually 4 KB of page sizes. So offset will be, so the 4 KB of page size means how many page size, what is the page size of the coarse table? It is 1 KB, correct? We saw that. If the page size is increases, individual page size is increased, then the table size will come down. So it is 1 KB size. So it is mapped onto some location which is the 1 KB boundary. So actually these entries give where the L2 table resides. Okay, it is a starting address of the L2 table. Please remember. Then within that, how those 1 MB spaces access permissions are given, you have to go into access the L2 table. It is only giving the base address of L2 page table. If the L2 page table is a fine table, then the lower bits will be having 1 and this is fine table means it is a 1 KB pages. 1 KB pages means how many entries? Because there will be 4K entries will be there because it is corresponding to 1 MB. Okay, 1 KB is corresponding to 1 MB, and how many entries will be there? 1K entries will be there, but it is actually 4 bytes each, so 4 kilobyte of the size. Okay, so that's why it has to be on a 4 KB boundary. So 12 bits will be not ignored here. This is the starting address of the L2 fine page table. Starting address, okay, because it is on the 12 bit boundary. Because the size is 4 KB. So if the page size is small, the size will be more. If page size is bigger, the size of the page will be small. So accordingly, the number of bits it occupies to give that starting address will be different. Now, why this is required? With all these zeros, it indicates that that virtual space of 1 MB is not mapped to any valid space in the physical memory. See, if we can represent all 4 GB, okay, to a valid space in physical memory, then you don't need a MMU at all, right? You have all the physical memory of 4 GB. That is not the practical case. Anyway, all 4 GB is not going to be represented in the physical space. So, but virtual space will have all 4 GB. So we have to have entries, whichever is the hole where there are no memory available in the system, we have to make an entry like this. So that in case if ARM processor generates such an address, it will be caught. That means it will, if a fault happens, then MMU will generate a data abort or prefix abort to patch that data. So I hope this is clear to you. So this is the 190 section, okay, and this is a 4 KB boundary. This is a coarse L2 page table. If page size is more, the table size will be less. Number of entries will be less, so the table size will automatically be less. That's why only it is a 4 KB boundary because the size is 1 KB. And if it is a fine page table, it is a 4 KB of size, the page table itself, so it will be on 4 KB boundary. Okay. A fault entry generation abort exception. That's what is here. But why there is nothing entry here, no entry here? It is actually not pointing to any section, or it is not pointing to any table. So as soon as the MME looks at this, it is a don't care. No, MME doesn't even look at this entries in this spaces. Once it is 0 0, then it will know that it is where there is no valid entry, there is no, this virtual space is not mapped to anything physical, so we have to generate a fault. So MME generates a fault to the processor. Okay, good. Now there are two different controls to manage the task access. Primary control is domain. So in this case, I said domain is there. Domain is 4 bits are allocated for that. I am explaining that 4 bits what they mean. So primary control is the domain, and then secondary control is the access permission bit. So domains control basic access to the virtual memory by isolating one area of memory from another and carrying a common virtual memory map. So this whole, as I told you, this L1 page table has is mapping the whole 4 GB of virtual memory into some spaces in the entries in the L1 master table. Okay, so it has actually each area of 1 MB is mapped to. We can give a different domain and then control it differently. When domains are assigned to a section, it must obey the domain access rights. Domain access rights are assigned to another register. Okay, because domain access rights. Okay, I will tell you. This register is having a 0 to 15, 16 domains are given. See, in the page table entry, you have only to say that a 1 MB section, okay, what domain it belongs to. Okay, it may belong to domain D4 or it may belong to D11. you are only saying which domain it belongs to, a particular 1MB section. But what that particular section refers to, what is its access rights are, is given in this bits. Okay, so each of them are occupying 2 bits. I will explain you what are the different entries that could be there. So you will know that how this domain can control a particular section of the memory. So this controls the code's ability to access the sections of the virtual memory. Now these are the entries. Okay, if it is the 1-1, access is uncontrolled. That means the section can be accessed by either in privileged mode or in a user mode. But 1-0 is unpredictable. Okay, it is not defined. 0-1 means access controlled by permission values set in PT. So if it was a L1 page table, okay, it's a section. If the domain says it is 0-1 present, okay, then if you remember there was a AP field also in the L1 master table entry, AP access permission. So as per the access permission, the control will be done. Okay, access permission to that 1MB of section will be controlled by the AP field in that particular PT entry. Okay, so or it could be a L2 page or L2 table also, which will also have a domain which is mapped to this. Then it will go by the access permission given in the particular page table. Otherwise, it is an uncontrolled access. So it is required sometimes to have a uncontrolled access to all the sections. So we can use this particular domain entries to achieve that. Okay, because once you change one domain, suppose I have so many entries in the page table, and then I want to control all the accesses using the domain entry. I don't have to go to every PTE entry to change those accesses, because I would have given the same domain. Suppose I have given a domain access initially to say that please go by what the PTE says. Okay, that is one way. Another one is I could have done that domain. So suppose if I have given a domain, for all these entries, domain as D13. Okay, so then what happens if the domain value says it is 13th domain, then the 2 bits here will there will be so many entries with the domain 13 in the page table. All of them will fall under. It will follow what the access permissions are mentioned here. So if I come here and change, initially I have given uncontrolled, and then later on I make it 0-1. What happens? It will all be controlled by the AP. Then suddenly I want to decide that don't go by PT access permission. I want to have uncontrolled access to all the pages in the system. I need to do only a change in this particular domain 13. I will make it 1-1. I like it to using this co-processor. I 1-1. Then what will happen? The page table entries are not considered at all. Okay, they will remain there, but they are not considered for access permission, and we will have uncontrolled access. So OS can have a control on multiple pages by just changing the domain entries here. Okay, it needs a little bit of thinking to relate to it. Please remember, first access to a particular page table is seen by the domain value, and then based on the domain what it is set. Okay, we could have represented one of the 15 domains we could have given, and then based on the domain entry a page table access permissions are considered. So all the entries in L1 as well as L2 will have both domain as well as the page table entry access permission will be there. Whether to consider this access permission in the page table entry or to have uncontrolled access is what the domain is deciding. So I can put some domain values in some set of pages, and then if I come and change those values to either 0-1 to 1-1 or 1-1 to 0-1, then I can have access to all the pages with one minor change. Okay, this is what is the need of the domain. So one program can be a client of some domain and a manager of some other domain, and have no access to the remaining domain. So program particular virtual space, it could behave as a different domain, and that control also you can have. Okay, that is what about L1 page table and domain. Now let me tell you what L2 is. As I explained to you, these entries I have already explained. So let me go through that. When L1 table is acting as a directory. Okay, so if you recall, the lower 2 bits will say whether it is the L2 course table or find table, or a fault entry, or it's a section entry. So if it is one of these two entries, then it's a directory to L2 table. So L1 PT contains a pointer to either an L2 course page table or L2 find page table. It could be one of them, not both. It could be one of them. So both tables represent 1 MB of virtual memory, and one entry in L2 course PT points to 4 KB page sizes, and L2 find page table 1 KB page size. So as I told you, the entry where in course table points to 4 KB page sizes. In find page table, it will be 1 KB of page sizes. So when a higher page sizes are to be supported, similar entries are stored in multiple pages. As I told you earlier, these higher sizes are represented by having a similar entry. So if you want to have a 4 KB page, okay, of no write access, write back access, and then buffering we want to have, then these access permissions can be entered in all the 4 page table entries, and all of them will have the same access permission. So that's what we are saying. We can do that. So an example, 4 KB page size in find L2 table has 4 similar 1 KB entries. Similarly, 64 means it will have here 64 entries, similar entries. That's it. Okay. A large page entry defines the attributes of 64 KB page size. Okay, there's a large, we call this a large page. That is 64 KB of page frame is called large. A small page is a 4 KB page frame. That 4 page KB, frame is here. Okay, and then a tiny page is called 1 KB page frame, which is the fine entry in L2 table. The fault page entry generates a page fault about exception when accessed. Okay, now let me explain this. Okay, up to this point, okay, 1 MB of space. Okay, this is 20 bit. Okay, so 1 MB of space. So whatever is below that offset, using this register, okay, we access the table and then try to set that 1 MB of space, whether it is pointing to a physical location, okay, or it is pointing to some directly. It may be pointing to a physical location, or it may point to a L2 page table. Based on this entry, we know that it is the L2 page table, okay, and of what size? Course size, because 10 is the 01 is meant for course page table. That means what? Course means 4 KB of size. So 4 KB of size means once we get an entry from this points to an index here, and then we can get the base address of the table from here. Okay, and then index we are getting it from the remaining address, because this 1 MB space only is divided into 4 KB, right? So that this portion corresponds to 4 KB. So this will be an offset, will make you access the particular entry in the table, and then we will know this 4 KB is mapped to which location by looking at this value, which will be anywhere, any value here. So it can be anywhere in the physical memory. You will get that particular address, and then you add that offset value to access a particular page. So effectively, in the virtual space, wherever this 4 KB is lying, okay, may be made to look, to be placed in anywhere else in the physical memory. And then it will not only say where this 4 KB is lying, but also this table entry, this entries we are not seeing. This I will show you. This will be giving you access permissions to that entry. Okay. So why do we need only for this co-processor, and then we don't need a co-processor entry here? Because we are getting the table base address from this page table entry. So each of those entries in the master table, if it is pointing to another L2 table, it will have the physical address where it is, the particular table is located. And then these are all physical addresses. Okay, whatever you are getting is physical addresses, but it is not using the MMU here. It is directly mapped to physical addresses. So you get to access the L2 page. From there you get the actual physical address from there, and then add the offset to access the exact particular location in that particular page. Okay, I hope this is clear to you. A little complex, but you have to look at this slide, look at what is happening, and then all the explanation that I have given you, so you will be able to internalize this particular thing. Okay, let me explain some more. So each of the L2 page table entries can be of this. If it is a large page, Okay, um, it will be 64 KB of page table size. L2 page table size will be 64 KB because if it is a large, a huge page means 64 KB of page size. So that 64 KB of page size, you need to keep 16 bits not needed, only the higher values. So we will use this physical address to access that particular page. Once the 64 KB page is accessed, the access permissions are given here. They are given four different access permissions with that 64 KB, okay. So here, how many bits are there? 16 bits, right? Okay. 16 bits. This corresponds to 64 KB of page. That 64 KB of page is split into four areas by giving these access permissions there. So you will be able to control it at the, even though it is 16 KB, you will be able to control it at the granularity of 4 in terms of access permissions. Okay. Now what happens to the small pages? The page size is small, 4 KB page size. So that's why you are saying that 4 KB. Out of the 4 KB also you have different access permissions for different. So you can decide to have within the 4 KB page, all the 4 KB will we have the same access permission or different access permission based on the value. So AP0 corresponds to this location as in similarly AP1. So this whole thing can be belonging to one task. Okay, but this can decide a code, this data, this may have a tag. Then you can define the access permission according to the where what you are placing in each of them, and then where exactly they are located. You can give it in this base address. So complete access control is there for a particular page of size 4 KB. And even though the page size is 4 KB, you have a finer access permissions if you want to. Otherwise, you can give the same access permission to all the entries. So they all 4K page, 4 kilobit of page will behave the same way. Tiny pages, you don't have any more final granularity other than more than 4 KB. So all 4 KB of page is given a same access permission. That's why you see that only one entry is there. Okay, they are not gone to the extent of splitting into some more 512 bytes or something that which is meaningless. So all 1 KB of size is given the same access permission, and then the behavior, cache behavior, and buffer behavior. So all these entries are again similar to L1 page table are zonized based on the lower two bits. Okay, and then the exact physical address is given here based on the page size. The physical address length will be defined. 4 KB page size, you will have bottom 4 KB because the offset is coming from the directly from the original address generated by the processor. Remaining location only you want to know where exactly located. So the base address is given for a page, and then rest of it is used for access permission or no, it is not part of the address. Okay, it is only this part is actually is filled by the offset coming from the processor address. So the remaining is page part. If it is 00, if some entries are 00, there is no physical memory present for that address. So PT holds the base address of page frame, and then the entry also includes 4 sets of permission bit fields and the cache and write buffer attributes for the page. So each of them will be mapping to a from the lower address to the higher address. Okay. I hope this is clear to you. So let us see that the access permission bits are similar to what we saw in NPU. Read, write, privilege mode, and then user mode. Different combinations can be there. And then the cache behavior and data behavior is combination of these two bits. We say not cached or not buffered, not cached and buffered, and cached and write through. If it is cached only, you have to say whether it is write through or write back. If it is not cached, we have to only say whether it is buffered or not buffered. That's all. Okay. So this is how the control goes. So MMU finally after initializing all the registers, we may have to enable those cache, and then MMU. Okay, so those bits are write buffer, those bits are set finally, and they are located in this particular coprocessor address, and then we can have instruction cache enabled or disabled, and B is another which I have not told earlier so far, because I was saying the vector table can be only at this location, but for some systems we cannot keep memory in this address and we want to keep some flash or something or some other memory in this higher address, then we can locate the instruct vector table at a higher address. Okay, that is choice the system designer, and only they have to take care of setting the V bit. So these are all supported only in these processes, not at the layer version of the processor. Okay, so this is how we have to finally do this to enable after programming the memory registers and tables are built and then they are initialized, you are good. So how we can do this? A typical system is like this. So kernel region, fixed addresses. What do I mean by fixed addresses? This is mapped directly to the physical address. So there is one-on-one mapping. So MMU is not needed to access any of them. So page tables can be accessed and any shared code or data can be accessed, and then system code, that is OS code, is here. And then the rest of the task physical location is here, but their task region is in this address. Okay, all of them are mapped to the same physical address, but they will have a different page table entries to point to different locations in this. And then we are not using this space, and then the peripherals are mapped to this. As I told you, the peripherals are mapped to memory addresses. So they are here, they are mapped to fixed addresses. So the whatever address we generate, it is mapped to the same location there. Okay, there is no memory MMU required for accessing this, because some of the physical peripherals we don't need to use, we don't want to use MMU, we want to directly access them. That also can be that. Okay, so dynamic addresses, this is a task region is always going to the page table, so that we can enable particular task at a particular point in time. So it's a typical example. I want you to go through the book where the actual implementation of this is given in the ARM Systems Developers Guide, which will make it more clear to you. Okay, what is the order in which we do? Define the fixed area of the system software regions. This fixed area is for keeping the system software and page tables. This enables to access them without the help of MMU. Please remember, that's what I told you. Define the virtual memory maps. This is what you have to do to set up the MMU. Define virtual memory maps for each task in the system, and then locate the regions listed in step 1 and 2. Okay, into the physical memory map. We have to decide where you want to map that into physical memory, and then define and locate the page tables within the page table. So you can TTB, those registers can be initialized based on where you want to place those page tables, and then define the data sets needed or entries needed for the regions and page tables. These structures are implementation dependent. However, a general form of this structure can be a good starting point. So this is implementation dependent. Why I call it implementation dependent? Because the physical memory where it is in the memory is it will vary from system to system. So you may decide to have a page table somewhere, you may decide to have a task running some other location. So these physical addresses are different. Accordingly, the MMU or page table entries need to be changed. So initialize the MMU and caches and write buffer, and then enable them. And then what you do, you have to have OS context switch routines gracefully transitioning from one task to the other. Okay, that's all. We have completed all the MMU related things. I hope this was clear to you. Let us go now. This is only one slide to tell you what is the tightly coupled memory. The system is designed to provide a low latency memory that can be used by the processor without unpredictability of cache. Why I say that cache will bring unpredictability means because of the kind of control flow there, the particular entry, whether it is there in the cache or not, is not in our control completely. It depends on the flow of the program. Okay, so because of that, what happens is if you don't want some routines to be affected by the cache behavior, we can say that that part of the memory may not be cached. Okay, and then we can keep it as a tightly coupled memory where the cache may not be coming into play. It will be directly accessed, and any write happening to the memory will be directly going to the memory. It won't be going through the cache. So that is the scenario. So such a memory can be used to hold critical routines like interrupt routines and real-time processing. Where we don't want to access the interrupt handling, some cache misses happening, and then memory access happening. We want directly to access the memory and it will be available. So teaching is used where indeterminacy of caches would be highly undesirable. In addition, it can be used to hold scratch pad data types whose proprietary properties are not well suited to caching. Typical data structures such as interrupt tags. Okay, we don't want them to be in the cached area. Up to 4 banks of data TCM and 4 banks of instructions TCM are supported by the architecture. Each bank must be programmed to be in different locations in the physical memory map. So I'm not going into detail because that will have another lengthy discussion. But need to be, it's enough if you know that there exists a TCM and we can configure a code data TCM and instruction TCM using some registers, and you may have to see the literature to know more about it. Okay. So with this, we have come to the end of memory management. So we talked about, we understand and understood about MMU and MCU, then virtual memory, translation request set buffer, and then I explained you about what are the L1 page tables and L2 page tables and how they can be located in the memory and how different access permissions can be configured in them. This is a very important part. I want you to look at this lecture again to multiple times if you don't understand in the first go, and read the book also, especially the book on developer's guide. That book will be good to understand them, and then look at the examples also to have a clarity. Okay, and I'm very happy. This is the book I was referring to. I'm very happy to share this information with you. Hope it was useful, and wishing you all the very best in your further reading this particular topic. Okay, take care. See you in the next class. Bye bye.